Hello, my name is Shivdath, and today we're going to look at a very interesting combinatorics problem to count the number of squares and the number of rectangles on a chessboard. So let me first quickly draw a very rough version of a chessboard. There's going to be 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6. So we have 1, 2, 3, 4, 5, 6, 7. I need one more. And 1, 2, 3, 4, 5, 6, 7, 8. Alright. So that's what my chessboard looks like. It's an 8 by 8 square. We have to count the number of total squares on it. If you want to work on this for a while, now would be a great time to pause the video and think about it. Alright, so if you thought the answer was just 64, well, the question is to count squares of all sizes, not just, 1 by 1 squares. So right, they're going to be 64 1 by 1 squares, but what about squares which are 2 by 2, for instance, something like this. That would be a 2 by 2 square, and 3 by 3 squares, and so on. So it's not as simple as just 64. Well, let's look at some edge cases. The biggest square is the whole board, right, of size 8 by 8. And similarly, the smallest square, the size 1 by 1, there's 64 of those, 8 by 8. So let's make a table of the size and the number. Let's say the size was 1 by 1. Right? Then we know that there's 64. Similarly, if the size was 2 by 2, well, that's a little more complicated. There's one here, there's one overlapping here, overlapping here, overlapping there. So let's leave it out for now. But if we go on, we know 8 by 8 squares are going to be 64, that's clear. What about 7 by 7 squares? You could think about this for a bit. It's not that hard, but 7 by 7 squares, basically, a 7 by 7 would just not include one row or one column. So really, starting at the 4 corners, you have 4 choices. One 7 by 7 would be like that, one 7 by 7 would be like that, one would be starting at the bottom left, and one is the bottom right. So there are there's one 8 by 8 square, and there are 4 7 by 7 squares. Now we could kind of use this further. But do you see any pattern developing in the number of squares? Absolutely. If you thought 1 equal to 1 squared, 4 equal to 2 squared, 64 equal to 8 squared, and you extrapolate, you're absolutely right. That's the pattern. But to be a little more rigorous, how exactly did we get that? Well, the way to look at it is, how would we get the number of 2 by 2 squares? We got the number of 1 by 1, 7 by 7, 8 by 8 just by eyeballing, by using common sense and doing some simple calculations. But how would we get the number of 2 by 2 squares, for instance? Basically, for a 2 by 2 square, right, we look at the left edge and we look at the top edge. The left edge and the top edge together will uniquely determine the 2 by 2 square. Now, how many choices are there for the left edge? Think about this and pause the video if you'd like. The answer is 7, because there's 1, 2, 3, 4, 5, 6, and 7. 7 choices for our left edge. And similarly, for each of those, we have 7 choices for the top edge using the exact same idea before. So there are 7 choices for the first edge into 7, or 7 squared, which is 49. And you could use the same argument for all other squares. In fact, you could have used that argument for the squares of size 1 by 1, 7 by 7, 8 by 8, and there would be no need for that eyeballing and guessing. So the total number of squares is nothing but 1 squared plus 2 squared plus 8 squared, and we know that the sum of squares of 1 squared to n squared, 1 squared, 2 squared, 3 squared, like that, to n squared, is nothing but n into n plus 1 into 2n plus 1 over 6. There are different ways to derive this. I might go over them in a different lecture, but you know, induction will simply work. You check for a base case, you assume it's true for n, prove it's true for n plus 1. That would be a boring but efficient and a way that works to prove this result. N is 8 here, so that would be 8 into 9 into 17 over 6, which is 3 3s, 2 4s, which is nothing but 204. So in other words, there are 204 squares on a chessboard. It would be, it's interesting to see if you were to just, you know, visualize it and not do any counting, if you could, you know, just come up with a guesstimate and see if your guess would have been close. You know, there's 64, and would you guess there about a similar amount of all other squares of all other sizes? Probably a little more, right? So we want a little more than 64, 2 times 64, or somewhat more than 128. And in fact, it turns out to be 204, which is quite a bit more. But you know, there are various ways you could kind of get bounds and get close to the answer. This method actually gives the exact answer. Now on to a little harder problem. Well, maybe not that hard, but find now the number of rectangles on a chessboard. If you want to think about it now, it would be a great time to pause the video while I erase some of the work done here. Alright, so the idea here is that the way we're going to proceed is first to look for rectangles, the number of rectangles of height 1, then the number of rectangles of height 2, then 3, 4, so on. And you know, a pattern will develop very readily from that approach. If you know, if you weren't thinking down that line that now you want to try that idea, now would be a great time to pause the video. Alright, so let's look at all rectangles of height 1. Right? So height 1 really means that we're looking at one row. So let's look at all the rectangles in that row. We're going to find n rectangles, n 1 by 1 rectangles, right? Squares are also rectangles, so there's n of them. I'm assuming the chessboard is of size n by n equal to 8 in our case, but you know, we could be dealing with an arbitrarily sized chessboard. It just generalizes the results. Now, how many rectangles are there of size n minus 1 by 1? Or how about, yeah, n minus 1 by 1? Let's see, so, or rather, of size 1 by 2. Let's take that case first. So how many 1 by 2 rectangles are there? Well, 1 by 2, we know 1 is coming from the height. So there's that same problem we looked at earlier of choosing, you know, from these n squares we need to choose 2 at a time. And remember, there were 7 ways to do that. We can go over that again. 1, you can choose these 2, or 2, 3, 4, 5, 6, 7. Note that they have to be contiguous. Those 2 have to be next to each other. So it's not 7 choose 2, it's not 8 choose 2 rather, n choose 2. It's not you're choosing 2 elements out of 8 possible elements, you're choosing them such that they're contiguous. That gives you 7 choices. So there are n minus 1, or 7 in our case, choices. N minus 1, 1 by 2. Similarly, there will be n minus 2, 1 by 3, and so on, till we get to n minus 1, till we get to n minus 1, and sorry, till we finally get to n 1 by n's, and n minus 1, 1 by n minus 1's. And the way we got that is how many 1 by n's are there? There's only going to be 1, right? So we're basically leaving the middle terms out in the sequence, dot, dot, dot. We wrote the first few terms, we're writing the last few terms. And we see a pattern develops from that. How many of size 1 by n minus 1 are there? Well, clearly they're only going to be let's see, so this should have been 2 and then 1 by n. I apologize for the confusion. So we're starting from n 1 by 1s. As usual, the first part was pretty clear. But now how many n 1 by n minus 1s are there? Well, this 1 is coming from the height, and to get n minus 1 we can either start from this edge and reach here, or start from this edge and reach here. So that's really 2 1 by n minus 1s. How many 1 by n's are there? Well, only 1, right? You know the height, and the length is n. So these are the number of rectangles of height 1, taking only this row into consideration. But there are n rows, right? So the total number of rectangles of height 1 is going to be n times this much. Or in other words, it's going to be, and so what this is nothing but n plus n minus 1 plus n minus 2 plus 2 plus 1, right? This equals this whole thing. But they're going to be n times that many, because there are n rows, right? So we get n times n into n minus 1 plus n minus 2 plus 2 plus 1. Now, similarly, let's look at rectangles of height 2. Now notice that the beauty of this approach is that we fix this height and our calculation remains unchanged for going across horizontally, right? Because now that we fixed that height, when we're looking at the horizontal length of size 1 or n minus 1 or n, you know, the analysis from the previous is going to be exactly the same. So this inside term that we're multiplying by will be exactly the same. But how many rows are there? How many cases do we have to look at of size 2? Well, when there's size 1 there were n. When there's size 2 they're going to be n minus 1. Because remember, again, that same argument. There are 8 rows of size, or 8 rows of size 1. There's 7 rows of size 2 when we're looking at them contiguously. 1, 2, 3, 4, 5, 6, 7. And similarly you can make the argument for 3, 4, 5, 6, it'll keep decreasing by 1. So height 2 is nothing but n minus 1 times this same thing. Similarly height 3 will be n minus 2, that same thing. And so what we get is nothing but number of rectangles is equal to the sum of all of that, which is equal to n. We're summing this out, right? So this term comes out constant. And what is this sum? This is nothing but the sum of the first n natural numbers, which is n into n plus 1 by 2. N into n plus 1 by 2. That's this common term. And then we're summing all of these up. N, n minus 1, n plus n minus 1, plus 2 plus 1. And the reason we have 1 is how many rectangles are they going to be of height 8? Let's just confirm this edge case. Well, 1, right? How many times we have to multiply? What's that factor? This inside term will be the same to see how much horizontal we're going. But again, there's only one way of choosing all those 8 together, all those n together to be more general. But what is this? This is also nothing but n into n plus 1 by 2, right? Again, the sum of the first n natural numbers. So we really get n into n plus 1 by 2. Or, these two are the same, so this is n into n plus 1 by 2 whole squared. And from here we can simply feed in the value of n and get the result. We'll get 8 into 9 upon 2 whole squared, 2 4s, 36 squared, which is equal to 1296. Notice that this sum, the sum of the first n natural numbers whole square, is nothing but the sum of the cubes of the first n natural numbers. So this is equal to 1 cube plus 2 cube plus 3 cube plus n cube. Another very cute and interesting result. May prove it in another lecture, but once again you can do it the steady, strong, but perhaps a little boring way through induction. Actually, sometimes this chessboard example is used as a proof of this fact, but that's just beside the point. So 1296 rectangles on the chessboard, 204 squares. I hope you enjoyed it. Thank you.